Okay, well, good morning again, everyone, and welcome back. Now's the time we're going to start our technical program. I've been working in sliding mode control and observation for a very, very long time, and also teaching and talking to students, academics, industrialists, training people to become familiar with the very latest concepts. I know a number of you in the audience know something about sliding mode control. Some of you may know a lot. Some of you may know not very much at all. I think one of the key things about my courses is I strongly believe we have to start together at the foundations, because it's by starting at those foundations we build a common language between us, which helps us to understand what happens when we deal with more complex systems, and also gives us ideas of how we can break away from standard approaches in order to solve those real problems. Frequently, it's very easy to develop mathematical results. Controlling or observing real engineering systems is a completely different matter. And sometimes there is not a one-one mapping between those two spaces. I strongly believe that good theory gives us good ideas, and we have to understand it deeply to be able to apply it in creative ways to solve more complex problems. And so what we're going to be doing in the two sessions today is we're going to be looking just at the control problem. So I'm not going to talk about observers. And we're going to develop those fundamental concepts so that we feel very, very familiar with the concepts. Now, there are some things I'm going to assume that everybody knows. And if anybody is finding it hard work after today should be relatively easy. By Thursday, we should all be finding it quite challenging. So it should be challenging us all. If there is anybody that by the end of today is feeling lost, there are a couple of things I suggest. One, of course, is you can talk to me. But the other is in the materials for participants, I presented some very basic background notes. So if you haven't had an opportunity to read those notes and you are struggling, please do that before tomorrow, because that will enable us to move forward very fast tomorrow. Okay, so the first session is going to be about me talking, it's going to be about fundamental concepts, and then the session after our lunch break is going to be all about doing, how we implement this in MATLAB, and we'll see how we go. I had hoped, but unfortunately we couldn't, I'd hoped to have the lesson this afternoon in a classroom where everyone could have had PCs and the same PC. We couldn't do that. Many of you have PCs, so that will be good. And we will see how we go with that one. But I'm going to start by giving you an introduction to sliding mode control, how it came about, why I think it's important. Sliding mode control was developed in the former Soviet Union as a formal theory. Over the years, working with industry, I found many control systems where people didn't know that it was a sliding mode controller, they didn't know it was a variable structure controller. They just knew that if they switched in some way, experience with their plant told them this was a really good thing to do. Switches are good. Don't let anyone tell you anything to the difference. We see them in the human body. They are throughout our human body, in our muscles, for example. The kind of simple variable structure controllers that were observed and analyzed in the former Soviet Union. If you look in the biological literature, similar controllers are in our bodies, which are very, very complex control systems. They have evolved through many, many years to be highly optimized, energy efficient. We find switches there. So never let anyone suggest to you that switching is bad. So sliding mode control started from this preliminary work in the former Soviet Union. It came from a field known as variable structure systems. So it came broadly from the field of switch control. And it really became very well known following the publication of a seminal IEEE paper which for the first time presented in English the fundamentals. And I'm going to begin by looking at variable structure control, seeing how sliding mode control evolved from that, and then looking at the type of general sliding mode control design paradigm, which is going to be a core theme throughout this course. It won't be the same canonical form. The transformations may not be the same. But at the core, this idea of how we seek to separate systems is very, very important to us. And so that is something we've got to become very familiar with. Right. What is a variable structure control? Well, it pretty well is what it says on the tin. The name is what it does. We have a control signal, and that control signal is changed or switched depending to some rules which are determined by the state of the system. So very, very general at one sense. It just means we can have more than one controller, and we decide which controller we apply based on what the plant is doing. And lots of people do that. So even people who design linear control systems for aircraft, they schedule them. They switch depending on the airspeed, the speed of the aircraft. So they are everywhere. Okay? Now, why are they a good idea? Why does our body use them? Why in those muscles do we have such switched variable structure controllers? Well, one of the classical examples that's used in much of the literature is to consider the double integrator, which is there in equation 1. Now, we know that a double integrator isn't straightforward to control. We know that in general, the more integrators we have in the forward path of a system, the harder it is to stabilize. And we see why. We use a simple output feedback controller where we're using more than one value of K. So on the left-hand side, we have some value K1. On the right-hand side, we have a portrait corresponding to K2. And we look at that double integrator and we say, well, yes, 2 integrators in the forward path, difficult to stabilize. If I use output feedback, I can't take a point, even in this nominal case, to the origin. If I look at what happens here from any point, if I start in phase portrait to the left here, to your left, I follow a sort of fat ellipse and I just go round and round the origin, getting nowhere nearer to the origin. And if I start in the second case, I follow this tall ellipse. So neither of those behaviors are desirable. They don't cause the point to go to the origin. And that would be a fundamental definition of stability. They're not disastrous either, because the system is not getting further away from the origin. But as we know, mathematics that we write down in terms of equations is always a nominal model. No modeler I know who is credible would say, my model is perfect. This plant will always obey this model. So we don't control models, we control real systems. Real systems are subject to uncertainty. Even if we know quite a lot about them the day we design the controller, they age, they wear, they become subject to disturbances. So any model such as equation 1 is likely to change. And if equation 1 changes in time, then these controllers that aren't dreadful could become problematic because this point may start to move away from the origin. Okay? So we would never build a control system using either of those two controllers. We've summarized here, the control law we've got is not appropriate since the y and y dot variables don't move towards the origin. There is some good behavior, though. There is some good behavior. Here we see, if we look in the phase portrait to your right, and look here where I'm pointing with my mouse, and we think of starting here on the y dot axis, we can see that the distance from the origin here is actually decreased in the first phase of operation. So the representative point moves around here and it gets closer to the origin. The problem is, once it crosses the y-axis here, it starts moving further away again. But there are some good bits of the behavior. If we look at the face portrait on the left-hand side, we can see that in this quadrant here marked B, if I start on the y-axis here and I move round, again the distance decreases. So I get closer to the origin. So a simple look at variable structure controllers could be to say, well, what happens if I have some control systems that have good parts and bad parts? And I try and build a system which takes the good parts of one and replaces its bad parts with good parts from another controller. And doing that with this simple example is oops. We have yeah. So I am in. Oh, I think I'm going to have to go back into the. We have a problem because I have used LaTeX for some of my slides, and it's a bit small on the screen, so I'm having to manually do it, and my fingers are sticky, so it's shooting all over the place. So this leads us to put together a control law which has two parts. Effectively, what this control law does, it takes the good parts of the first controller, the fat ellipse. So in quadrants A here, it uses this controller with the phase portrait on the right-hand side. And in quadrant B, it it uses the controller on the left-hand side. So it's splicing together those behaviors that cause the system dynamics to edge closer to the origin. Okay? And we can see immediately what happens if we do this. We can see that the motion goes towards the origin, moving along segments of long ellipses and tall ellipses as it moves through space. So here we see it moves closer to the origin. Rather than continuing with the fat ellipse, it moves to the tall ellipse here and gets even closer to the origin. And like a snail shell here, we spiral in towards the origin, and we take a system where the two composite systems themselves are not suitable, and we get something which is better. And that's a typical variable structure control system. It's not perfect. There are lots of things that aren't perfect about it if we think about it. This is incredibly slow. This motion going round and round is very, very slow. So for some systems, that might not be desirable. It's also rather heuristic. There are many types of controllers we could have switched between. Here, my hypothesis to demonstrate ideas to you was we took behaviors which were desirable, okay? So we took, the, if you like, the stable bits, the bits that were forcing the point closer to the origin. Actually, you don't have to do that with a variable structure control system, and it's quite interesting to look at some of the control systems from biology that switch, because they don't actually switch between two sets of good behavior. They might well use, for one of the phases of motion, unstable behavior. Why would we do that? Well, we would do that because an unstable system is very responsive, very maneuverable. My background, when I started in control many, many years ago, was designing control systems for combat aircraft. Combat aircraft, we require them to be highly maneuverable. We don't want something that's incredibly slow. In a fighting situation, that pilot needs to be able to maneuver that plane. And being unstable, with a pilot in the loop effectively making sure it doesn't run away to infinity, is just about as good as you can get. You wouldn't want it all everywhere doing that. I mean, when the plane is just flying from A to B with no problems, yes, you would want it nice and stable at that point. But stable everywhere is not always desirable. Unstable can be maneuverable, and there could be modes when we want things to be unstable. So the paradigm for this well-quoted double integrator doesn't really play to some real applications. And a lot of biological systems are actually like that, with an unstable phase, in order to be able to respond very quickly. They won't be like the pilot and the air piloting the plane and respond immediately. Typically with a biological system, it will wait for a while and make sure. It's highly energy efficient. Biology doesn't like doing unnecessary things. It's not like your typical microprocessor, keeping the error 0 all the time. It'll look at the error and say, well, is this really just something that's moving close to where I'm happy, or has something bad happened and I need to respond? And if it needs to respond and designed to respond, it will often respond in an unstable way. And muscles do that as well, in order to get quickly to pick up something. So there are a number of problems with this basic way of designing and thinking about variable structure controllers. Once we start to think about them, the class is almost infinitely broad. We've seen we can put undesirable things together and make better things, but we have to question, might it not be the case that sometimes we want phases to be undesirable, and the stability point is a good one. So it's not a perfect science, but it demonstrates very easily that what we can do is we can switch between structures. We can take things which didn't do what we wanted to do to start with, and we can make better systems. And that was a very powerful thing that was noticed in terms of the development of the science, if you like, the paradigm. But the conclusion is really that paradigm for most purposes is too broad. It's really hard to have a generic theory of variable structure systems. Okay? So people started to think about special classes of variable structure systems and other properties of variable structure systems. And this example gives us, if you like, our first insight into sliding mode control. And this comes very, very naturally by using a simple relay as the control. Notice we've made a change from what we did with the variable structure system. With the variable structure system, we were defining the performance based on the controllers we'd picked. The first thing to realize about sliding mode controllers, which many people who pick them up, we see many people in the literature who pick up sliding mode controllers as a tool. They have a particular problem and they try and apply it. But they don't realize that for a sliding mode controller, it isn't the controller that's giving us the performance. So this change, this motion from taking a variable structure control and moving to a sliding mode control in our early development really shows us that this is the case. Because I'm assuming just a simple relay. So all my controller is doing is switching backwards and forwards. So the controller is not defining the performance. And almost all sliding mode controllers are not defining the performance. And this paradigm that says the control is not defining the performance is very different to the paradigm of a typical controller. Almost any other control design, people design the controller and think of, well, I tune this parameter in the controller, I change the controller, and it changes the performance. In a sliding mode controller, we will see that for a given performance, you can have an infinite number of controllers that give you that same performance. So there is not a 1-1 mapping between controller and performance. And that's the first very, very important thing to take away from this. Here we're switching, and we've just defined a switching function which is a linear combination of the two states of the system. So all the way through this, I'm using the double integrator. So here I'm using the double integrator, two states, position and velocity, and I'm taking some linear combination of position and velocity, and I'm going to say m is a positive scalar, and we will see why very, very shortly. If we look at what happens with that system, we see in the phase portrait the same sort of transient we had before. This here, y dot plus my, is a straight line. So we can think it's very faint on the slide here, but I'm drawing now with the hand on my mouse here. That is the straight line y dot plus my. And I think I did this simulation with m equals 1. So if you want to make a note of that, if you want to try and reproduce some of the results here, this is just the simulation with m equals 1. And we can see that either side of that line, at least initially, the system is following effectively hyperbolic trajectories either side. So we've got a family of trajectories looking like a hyperbola here, a family of trajectories looking like a hyperbola here, and it's switching between the two families of hyperbole either side of that line. And it's switching until it gets to some point here, which we'll zoom in on in a minute, very close to the origin, where we see our point lies on the line. So there's no more moving around the hyperbole. It lies on the line. Now, why is that quite exciting? Well, that's quite exciting because if I look at the line I defined, y dot plus my is equal to s, that is a first order free dynamics when s equals 0. So by choosing m equals 1, I'm effectively designing via equation 5 a desired first order dynamics that I've chosen. It's got nothing whatsoever to do with the plant. So that is the second interesting point to note. I've chosen a dynamics. Okay? So I've chosen a very simple first order dynamics, and after some initial time, I exhibit those dynamics. And the evolution of that dynamics only depends on the time and the value of y and y dot when I first hit the line. So I hit the line, we can think of that as defining an initial condition, and the first order differential equation evolves from that initial condition. It's independent of the control entirely, the dynamics of the system. Doesn't depend on the control at all. It just depends on the pole I've chosen, the m equals 1, and it depends on the initial conditions, y and y dot, when I hit that line. Now, we might ask ourselves the question, well, why does it hit it there? And why did it follow the hyperbole? And the reason for that, very, very simply, is because of the magnitude of the relay we chose in equation 4. If we'd chosen to scale that switch by a slightly bigger number, so rather than switching between plus or minus 1, for example, we'd switch between plus or minus 10, then the region here would have expanded out. So bigger control action would have caused us to hit and stay on the line at an earlier point. So we get a notion of two phases to our dynamics. A first phase, which, yes, does depend on the control. A second phase, which only depends on the switching function. And the balance between the first phase and the second phase is very much about the magnitude of the control action. So the magnitude of the control action effectively says, well, for what values of y and y dot am I going to go straight to that line and stay on there? And for what values am I going to have a bigger transient when I'm following around these hyperbolae. We might start to ask ourselves the question, well, how do we know whether the control action is big enough? Because ideally, we want to get the dynamics we pick as early as possible. We'll see that there are bigger reasons for seeking to do this than just the fact that we get those dynamics. We will see that there are very good reasons in terms of robustness for trying to do that. But we can very, very easily see and determine conditions which let us develop the size of that control to be big enough so that first stage of the motion is minimized. And if you look at the literature, and if you look at different academics, different people, you will see numerous different conditions. There are lots of conditions. They're typically called reaching conditions, reachability conditions. And it's a condition to try and pick a control, fundamentally, choose a control U that lets you reach that dynamics S that you've picked. Okay? So it's about choosing the control to make the dynamics attractive. And fundamentally, they all collapse to the same thing in terms of physics. Because fundamentally, if we've got some dynamics, whatever dimension it happens to be, and we want to make that dynamics attractive to the system state, then we want to determine a control which will always make that direction of motion towards the dynamics we want. Because if the direction of motion is always towards the dynamics we want, it means we get there. We then might seek to move through the dynamics, but remember our condition is making sure that it pushes us back towards it. So the net effect of that reaching condition is going to be not just that I get there, but that I stay there. Because every side of that dynamics, I'm being pushed back onto the dynamics by the choice of control. And in this particular example here, we seek to explain why we get this two-phase type motion and how we can tailor that two-phase type motion. And we use the value of the switching function S and its derivative S dot. Okay? And the product of S and S dot, if that is negative, so the position and the velocity have opposite signs, that is a condition that's good enough to make sure that the direction of motion is towards the switching function. So if we look at S here, which is just S, and we look at S dot, remembering that S is my plus y dot, so we can differentiate that to get my dot plus y double dot. So that's the derivative of my switching function. And then, remember, I'm controlling a double integrator. So my y double dot is equal to u. But my controller is switching, depending on the sign of the switching function, plus 1, minus 1. So I can replace y double dot by u, and then replace u by minus sine s. Do some algebra and show that as long as my velocity here in magnitude is less than 1 over m, then SS dot is always negative, and I will reach. So we have defined formally the region in terms of the size of y dot, which would make sure that this controller stays on the switching manifold S we've picked. And in that case, they stay on the dynamics, the trajectories put on either side of my switching function point towards the dynamics, and high frequency switching between the two structures takes place. And that's the first time I've mentioned high frequency switching. And this has been a big bugbear, really, for sliding mode control, because in theory, we require high frequency switching. Okay? So for many of the theoretical properties we will discuss, they are predicated on high frequency switching. We have to realize that high frequency switching for some things is fine. You know, if I've got some power electronics, it can be switching at really high frequency, it's going to be fine. You see a lot of the literature using the controller through power electronics. Not a problem. Professor Badimutkin, the founding father, has done much work on control of those kind of things for electrical machines and drives. So it's not that high frequency switching is not sensible for everything. Some things is fine, and that's fine. But for some things, talk about my aircraft problem. You've got some ailerons on an aircraft. There's no way you want anything high frequency switching affecting those ailerons, because that will create fatigue and wear, will be dangerous, and is thoroughly undesirable. So much of the literature has spent time in trying to smooth the control. And I'll say at this moment, fundamentally what that means is, rather than bouncing backwards and forwards across that switching line, it replaces that dynamic with a smooth dynamic moving about the switching line. So you replace that discontinuity with something that moves smoothly. And there are hundreds of ways to do that. Many, many ways. And different people have their favorites, and I'll talk a little bit about mine later on in the course. But I'll already say why in this sliding mode paradigm, this control paradigm, which people spent a long, long time working on, has found it much more straightforward to get traction in the observer domain. And why we will be focusing tomorrow, and in some of our serious applications, on observer problems. Because for observers, of course, the switching makes no difference neither here nor there. An observer is sitting on a computer or some sort of embedded device. It's a bit of code. It can switch as much as it likes. And so what we've seen is, from this starting point, a massive explosion in applications of these kinds of ideas in the observer domain. And as I say, that's why we'll focus so much on this, because, you know, this switching problem for control, there are fancy things we can do. There are some novel nonlinear controllers that seek to provide finite sliding mode control, but they can be pretty difficult to tune for wide envelope performance. So there are lots of issues around this smoothing properties, but it's often good enough. You know, there's not many industrial areas where the tolerance is absolutely zero for your output. And so if you design your smoothing strategy in line with the design tolerance of what's acceptable for your error bands, then it can be acceptable for industry. So it's not brilliance in terms of a property, but it's often good enough. But we have to recognize what's good and bad about what we're doing and why. So, here on my big graph, we see in detail what's happening in that ideal situation where our controls effort is big enough, so we've got sufficient energy in the system to ensure that we can move. In this case, I think it was from y is 1, y dot is 0, straight onto the sliding surface. That clearly satisfies the constraint for m equals 1 that we had. And then it moves into the origin along the dynamics with the pole at -1, which was what I picked. And it's nice and smooth because I implemented it with a smooth control, action. Now, what have we done so far? Well, what we've done is we've taken a double integrator, which is second order, and we've made it look like a first order system, and a first order free system at that. So it's a system which I pick, and that only up to the initial conditions is wholly determined by my choice. And that's often a good idea. You know, frequently having reduced measures, if you like, people can think, oh, it's good to have lots and lots of parameters to tune, but when we're dealing with complex systems, having 101 parameters to tune is not necessarily desirable. It can be too much design freedom. We don't know how to deal with it. I can't stress to you enough that this difference between what the control is actually doing in sliding mode control and that it is not giving you the dynamic performance. It is purely satisfying a reachability condition. So there are many control systems where they satisfy some inequality, okay? You know, that SS dot less than 0 for some U, I can choose loads of U's that would satisfy that. And the performance would be the same because it's wholly determined by the selection of S. Okay? And that's really, really important. There's lots of people that spend lots of time fiddling around with their controller trying to affect the performance of the system. That's not the approach. The only thing that will check, when we do our MATLAB this afternoon, we'll see it. The parameters of S will just determine that reaching phase, how fast it is, whether it's oscillatory. So there is usefulness in looking at that, but that's all it does. It's the choice of S that will limit that performance. And I think that's a good enough summary. I suppose the big question then becomes, well, why would we bother? You know, yes, we've reduced the order. Yes, we have taken something which is very simple to design. It's just a control signal that needs to be big enough and a performance that we can pick. But would that be enough? Well, I think the answer is probably not. The key reason why sliding mode control and observation have become so popular is all around robustness. And that's why these control systems in the human body we mentioned, such as muscles, where I said to you, switches are indigenous. We see that has also evolved because it's robust. As we'll see later on in the course, interestingly, our observation from sliding mode control about is the control big enough, Does it satisfy something in terms of a reachability paradigm to make it do the right thing? This explains and can be used to explain the evolution of some diseases. Because the switches in the human body, effectively, for whatever reason, someone's immune compromised, someone gets subject to some highly undesirable virus or whatever, it takes these switches in the human body, and just as in the variable structure control, they are insufficiently large to attain the performance that we need to be healthy. So very, very important in terms of the robustness that we get from these switches. So robustness is the order of the day. And the simple way to introduce this is to take the double integrator we've been dealing with up to now and look at a perturbed one, which in terms of a perturbed system is just a double integrator with some uncertainty, which is sinusoidal. We can scale it, and it becomes a double integrator. So it's a nice one to do. Here you see the dynamics. I'm not using friction in my model. And so you can see that theta double dot equals something dependent on u in the final term, and then this sinusoidal term. Okay? So if I scale it appropriately and scale the control, then that is just a double integrator perturbed by a sinusoid. So it looks like this. And as soon as we start looking at that problem, we can say, well, it reflects the situation which I said to you was the normal situation for a controller design. I don't know what you find with your undergraduate students, but I have my undergraduate students, they're excellent students at UCL, some of the best in the country, in the United Kingdom, very mathematically adept. They want to come and learn and pass their exams and do really, really well. So they solve control problems based on equations highly efficiently and get controllers. And it's always a shock to them when I say, well, yes, but that's only part of the problem. That's a good thing to be able to do, but we've always got to remember that control engineers aren't in the business of directly controlling equations. We're controlling real systems. So the difference between our pendulum here and our double integrator, for the purpose here, we can assume it's the difference between a model used to do a design, where we've used, say, a small angle approximation to get rid of the sinusoid, so an approximation to control something that's real. Now, what happens if we apply the control law, exactly the same one that I used in the previous example? So I used the same controller and the same initial conditions. What do we see? Well, we've got two traces here. The dotted line here is the nominal system, so that's the system without the sinusoid. The solid line here is the pendulum, the scaled pendulum system. So we see initially there is some deviation. Not that different, so it's nothing drastic, but it's certainly different. Why is it different? Well, it's different because the dynamics are subject to the sinusoid. So the sinusoid is present. It hasn't reached the sliding mode. We notice it reaches the sliding mode at different points, but once each of those entirely different systems has reached the sliding mode, they exhibit exactly the same dynamics. y dot equals minus y, fundamentally. So the sinusoid is completely rejected. So people think, and in the early days of my career, I used to have it was a time in the UK where many people were interested in robust control, H-infinity control. That was just being developed. And so they were very interested in norms of disturbance signals, minimizing norms of disturbance signals. So they were convinced that I must know what the signal was. They said, you cannot possibly have a signal in there, which is a sine wave varying, where the dynamics, you don't see it. There must be something, some norm that's somehow coming into play there. You just can't do it unless you know what the sinusoid is and you're cancelling it out directly. So you must be cheating. And so I say, no, I don't know what the sinusoid is. I have a switch, and the switch, if we want to know, begin to think about why this happens, well, the properties of having a switch in our system, it's why it's so positive, is actually giving us the properties that you might see with infinite gain in a purely linear system. So it's mapping that infinite gain, which of course is entirely unrealizable. We can't implement a controller with infinite gain, but we can implement a switch. And the switch has the same robustness properties. And that's incredibly powerful because it's almost not robustness. It's invariance. It is not depending on it at all. And this is really at the heart of why people want to know about sliding mode control, because the capacity to be able to take systems and to exhibit this kind of robustness becomes incredibly important. We've only done it for a very simple system here, but just think of the potential. If you have got a highly large-scale interconnected system. So all of those interconnected systems are going to be affected each by the other. So there's going to be effectively signals coming in, perturbing those systems. If you have the potential to collapse the problem down so that you can accommodate those interactions by appropriate choice of control, then that is very powerful. Fundamentally, for complex interconnected systems, at the heart, people always want there to be some control that keeps them stable. Something that makes sure they're stable. And we can't ignore the interactions. But if we can take care of the interactions with fairly local information, which again gives us robustness if we're not having to pass lots and lots of information between different dynamics to implement the controller, we can design controllers that make sure these large-scale systems remain robust. Okay? And that's just one example of the kind of nonlinearity we might have and where we might wish to use this. So, how does it do it? It's really quite straightforward in terms of a paradigm. We've just taken a system, we've defined a dynamics, we've made sure the control is big enough to ensure S and S dot have opposite signs. And clearly in that calculation, we saw the calculation we did for the double integrator without uncertainty. In that calculation, the size of the disturbance will come in. So we already can picture in our minds from the structure of the mathematics, definitely from what we've seen this morning, but maybe using our knowledge anyway that we brought to the course, that the size of the control is also going to have to be modulated by the norm of that uncertainty, because we need to still ensure that SS dot has opposite sign, and that SS dot equation will be determined and affected by the uncertainty. This so this is very powerful. What we have to think about is, well, this is all very well. She's taken a double integrator. She's put a sinusoid there. She's waving her arms and saying we can do this for large-scale systems. But how are we going to do this for more general systems? How do we create a paradigm of sliding mode control? Well, it really is very simple. At the heart of this, we just have to think about the stages we had. The first important stage is the design of the switching function. So we need to have a means to design switching functions. We need to note that's independent of the control. So in terms of solving a problem, we like to think about how we can think about systems in terms of bits of the system where the control acts directly and parts of the system where the control doesn't act directly. Okay? Because we know for that switching function design problem, it's not a function of the control. So it's much easier to do it if the control isn't there. So the first thing we need to recognize is that we need to partition the system. We need to partition the system into bits where the control acts and bits where it doesn't act. And if there are general ways of doing that, that's positive. Okay? And having done that, we can use the subsystem where the control doesn't act to design the switching function, and we can use the second subsystem where the control does act very simply to solve the reachability problem. And then we can begin to think about, well, why is it robust? Well, I think it's intuitively obvious how it's got to be robust. I mean, my colleagues from the H-infinity control community were not wrong in that they said to cancel the signal exactly, you need to know what it is. That's clearly the case. Where they were wrong was that they thought I was using that information directly to cancel the signal. What in fact was happening was by the properties of the discontinuous control signal, on average, what that was doing is reconstructing the sinusoid. Okay, so on average, it is giving you the measure of the uncertainty exactly. So it's cancelling out the signal, but it's cancelling out by the property of the control signal, which is, although it's switching about, and we'll look at some examples where we see just a mass of switching, that if you take away all that discontinuity, what that switch control system is doing on average is reconstructing that disturbance signal and playing it back into the dynamics to enable it to disappear exactly. And that's very important property. It's not just important in that it gives us robust performance, but it also lets us measure uncertainty. It lets us measure faults and failures. It lets us measure changes in the system by looking at what that applied control signal is doing on average. So that has huge potential and will be something we will develop very much so in our course. But first of all, let's look at what we need. So as I've hinted, we've got this reduced order motion which doesn't depend on the control. It only depends on the surface, and that's the first thing we need to be able to do, is to pick that And as I've said, to be able to remove the control from that sub-problem seems a sensible thing to do. The second thing we need to do is to satisfy some sort of reachability condition. So as I say, you'll see many in the literature. We'll use different ones as we use more complex systems and go through the course. But fundamentally, they all have at the heart number 12, which is that the direction of motion is different either side of the line. Okay. I think one thing I would like to say at this early stage is when I started my career, and I think that was because we were frequently looking at designing controllers for elements, relatively small things. There was a great focus on finding an algorithm, finding a method where you just took some systems, and at that time it was frequently linear systems, and you determined a controller. And we will do a bit of that within our GIAN course here. But I would encourage you to think more about these principles of what we're trying to do in a wider way. If we're designing control systems for complex systems, we're not going to be able to find a really simple canonical form that we can apply to all systems and which is going to produce a controller. We need to be able to think of design from the point of view of what we're seeking to achieve and some of the things that we know about fundamental principles. There's a new report that has recently come out from the International Federation of Automatic Control, which is looking at control moving forward, and is hypothesizing a new paradigm, okay? So that we shouldn't just be the people that come in and do a model when control systems are needed because systems that have been designed for other purposes fail. That's been the classical paradigm, really, for control people. You know, somebody's designed this. They now need it to do that. You're a control engineer, you model it, you put in a feedback loop, and the problem goes away. The IFAC report hypothesizes that the times are changing, that motivated by these very complex systems we have, humans in the loop, huge problems, spatially distributed. You know, we're not looking typically at a generator these days. We're looking at a whole ecosystem for energy involving consumers, involving markets. We can't let other communities go away and do things and then find they don't work, and then we have to come in and try and do other things. We need to be getting involved in those problems as they're being set up and structuring those problems in ways that we know are good from the point of view of control. So, you know, I think my students will have a different career to my career. I can see what's going to happen. I can see what's needed. I think there's going to be a paradigm shift for all of us involved in control, as is in that report. But having said that, we're going to do something quite classical to start with, just to get you going. But I suppose what I'm saying is, keep your eye on the bigger picture. You know, what are we saying about systems? How can we extrapolate this into how we design bigger, better systems, or indeed even understand systems that might be good? I mentioned to you this property that on average the control signal is counteracting the uncertainty. This is known in sliding mode control circles as the property of the equivalent control. And the equivalent control concept really explains why the system is robust. And in lots of the work we do, we talk about the equivalent injection signal. So we talk about a signal which is effectively measuring the uncertainty in our system. And so this little bit of analysis really explains why our double integrator can reject the uncertainty. So if we look, we've got just the same control I had before, the relay control system. We've got our first order switching function, and we notice that in the sliding mode, effectively S and its derivative will be 0. If we stay at S is 0, then effectively S dot must be 0, else we wouldn't stay there. So if we look at S dot and see what happens when it's 0, we can see that there's an effective control law that is the thing that maintains the sliding mode. Now, it's incredibly important to notice that equation 14 is not the same as the applied control. And this is a very important thing. I see all the time. I saw a very recent piece of work by industry, where industry had used this, effectively, the equivalent control, as the applied control. The equivalent control is a theoretical construct. We should never use it directly in our controllers. I would advocate never using it directly in our controllers. It is a theoretical construct. It mimics what this control signal here is doing on average. So this is the real control. This is what the control signal is doing on average in order to maintain the sliding mode. And if we look at trying to make sure we can guarantee sliding, we can take our system here and we can see, which we didn't have in the previous example. I just said let's make it big enough. I was slightly arm waving. So now we build slightly more detail in here. We put in S dot. We can see that in general, to make our control big enough to ensure S dot is less than 0, there's going to be many, many control laws I can define. But the first thing we do is initially think of doing something which removes parts we know from this equation. And that's where people go wrong. They tend to do that with the equivalent control, and sometimes they're the same, but sometimes they're not. Okay? So here I'm applying something that looks very like the equivalent control, but effectively I'm applying it here because I want to simplify this reachability condition and get rid of parts I know. Why might I want to do that? Well, one of the reasons why I might want to do that is it isn't necessary to do that. I could just put a big switch in there. But if I use a big switch to counteract things I know, I'm exacerbating the chattering problem. I'm making the chattering problem worse because I use a big switch to counteract bits I know. So to me, that doesn't make sense. So in my designs, I always use an element which exploits the parts I know from the dynamics and seeks to get rid of them. If I know what they are and they're impacting on my reachability condition, why not cancel them out directly by the choice of control? Then, having cancelled them out directly by the choice of control, my switch can be smaller. My switch is only providing robustness. It's only dealing with uncertainty. And that means my chattering problem is less problematic. So my chattering problem becomes much less of a problem. I have less chattering to alleviate. You'll see I have a completely different style when designing observers, because as we've said, when designing observers, it can be as big as I like because it's just on a microprocessor. But as a control engineer, we have to be, how shall I say, sensitive to the constraints of the control signal. So getting rid of nominal parts directly is a really good thing to do, and seeing how we can do that, and then just using a bit of a control signal, the switch element, to counteract any uncertainty. Now here we've got no uncertainty, so for very, very, very small values of gain, only dependent on the parameter of our system B, we can ensure that we meet that sliding strategy. But it's an art, not a science. And there isn't really a right or wrong. You know, if you look at the literature, you see many different approaches to solving that reachability problem. With everything I do, all the way through the controllers, right to the end of this course, you will see my method, my approach is always to cancel anything I know that I can deal with directly with the control to do that, because that makes my control maximally efficient. Okay, so if there's something there that I know is impacting and I can measure the signals associated with it, I get rid of it. There's no point. Yes, the discontinuous control action can deal with it, but it won't give you a good control properties. Your dynamics will look the same, but your control signal will have much greater switching, and there will be a much greater need for smoothing. So I only use the robustness to deal with anything that is uncertain. Okay, so having talked a little bit about the control, we must make sure the reachability condition is satisfied. Why do we do that? Well, if we want the system to be robust, it's got to reach the sliding surface. Those properties of the equivalent injection don't hold until I'm lying on S equals 0. If I spend a whole lot of time going round and round or doing something different before I get here, then I'm just the same as any other control system. I'm affected by the uncertainty. I'm not invariant to that uncertainty. And so I need to minimize this effect as much as I can within the constraints of the uncertainty. Clearly, if the uncertainty is massive, my control in magnitude, my control signal may not be big enough. And so I might have a bigger transient before I hit the sliding mode. I would say in cases like that, it probably means your sliding mode is not the best choice. Some people think, well, we just have to choose a linear one. Lots of the literature does. But we don't. So if we had something where it was a long way away from this kind of linear dynamics and we had difficulty reaching it, well, why not create a non-linear sliding surface that had these sorts of dynamics close to the origin and had some dynamics that stretched rather better to take you to take you to those dynamics in a robust way. by having a nonlinear sliding surface. So there's nothing to say they have to be linear, and there's everything to say that we make the reachability problem such that the reaching time, the time till we hit the sliding surface, is small, because only then are we robust. So, a plethora of designs we can use, and in my career I've used all sorts of designs of both sliding surfaces and controllers. So just before we think of our lunch, I'm under strict instructions from Sohom that I've got to have finished by 1 o'clock. Let's talk about how we might take this into a state space formulation. Now, ideally, we've said what we want is to partition away the space where the control input acts from the space where it doesn't act. And the starting point that I'm going to use for ease of exposition here is going to be the linear state space system in number 16. And I'm going to have a linear function of the states as my sliding surface. I am restricting myself here to a single input problem, but we will see that this readily scales, and we'll be happily dealing with multivariable problems by this afternoon. We're trying to make sure that we can force S to 0, and that when S is 0 and this ideal sliding mode is taking place, then that we have dynamics that we want. But as I've hinted, bear in mind that this is something we can do, and indeed will do throughout the course, for much more than a linear system. But I think it's important to get the ideas. One of the reachability conditions, which I've said most of them are a special case of SS dot being less than 0, is the so-called eta reachability condition. We use this a lot. We still do use it. We can see that if this is satisfied, then it clearly is a special case of SS dot being less than 0. I like to show this example. I think it's nice and intuitive because it shows the reachability. It shows the ideas for something that didn't come from a sliding mode perspective. I think, I've talked several times about the control systems within the human body, muscles, the immune system. I think it's good to see this isn't just a mathematical puzzle. That there are systems where this becomes, if you like, a framework for normal, natural, sensible operation, which I think gives it credibility. So let's think of a water tank where the water is at height h, and there is some outflow. We know, or we can model the flow rate through the outlet as being proportional to the square root of the height, and we can write down a differential equation that governs the height of the water, and clearly that's going to depend on the cross-sectional area of the tank. If we write h, our height, as s squared in 19, so s effectively is the square root of h, then naturally we get from this system the reachability condition. So this is a motion which naturally exhibits the reachability condition. So, you know, the reachability condition is not so, you know, people say, oh, that, you know, they choose mathematical things. You know, it's mathematics, it's subject to assumptions. Well, actually, a very, very simple system based on physics has a sliding mode and satisfies a reachability condition naturally. Now, in terms of thinking about the design, let's just think of a particular case for a moment. It's a real system. It's the equations of motion of a hot air balloon. It's taken from one of the undergraduate control textbooks, but it's easy because we can, you know, think about the calculations by pen and paper. It's also nice because I said to you that a key property is going to be that the channels where the control acts and the channels where there is no control should be separated. And this system actually has that structure to start with. Okay? So the model has the structure where the control signal acts directly on the third state, but there is no impact of the control signal directly on the third state, on the first two states. The control signal only impacts on the first two states components via the third state. We can see that such a system needs a controller. It's got a pole at the origin, so it's not desirable. Let us think about selecting a sliding surface, and let's think about taking a linear combination of those three system states. Now here, note that that's defined by two parameters. If you think about previous example, I was trying to control the double integrator, which was the second order system, and I picked one parameter, m, the slope of the sliding surface, to define the dynamics. Here, the number of parameters has reduced by 1. Why will that always happen? Well, it's intuitively obvious. We could leave 3 parameters in there, S1, S2, and S3. But remember, the objective is to make S times X equal to 0. So this thing here is going to be equal to 0. So if I've got a parameter S3 here, I can always scale S1 and S2 by 1 over S3, so it has no effect on the dynamics. So we make sure that the number of parameters we choose to define our sliding surface is a minimal set. We don't want to be having parameters to select that are dependent on other parameters, because that is not helpful for our design. So that is why we drop the parameter value to 1, because if we included it, we could always have chosen an S1 and an S2 that would give you the same dynamics. So if you can solve the problem and get the same solution by choosing 2 things rather than 3, why would you choose 3? Okay? So we choose a minimal set. And we notice quite naturally that in this sliding mode here, when S is 0, X3 is dependent only on X1 and X2. So when S is 0, I can rewrite X3 in terms of S1 times X1 plus S2 times X2. So this splitting of the problem has effectively taken part of the state vector and said, well, for my subsystem, that part of the state vector X3 is effectively a control. So I've got a reduced order problem here where we can think of this, the 0, 1, 0, minus 2 subblock as defined in the dynamics, the 0, 1 as defined in the input injection matrix, and X3, which is the thing that post-multiplies 0, 1, being given by minus S1, X1 minus S2, X2. And this is what I've done here. So we can see we've written down S equals 0. We've expressed X3 in terms of X1 and X2. And we can see that the design of the sliding surface just becomes a control problem, a feedback control problem for a control X3 that is applied to the remainder of the system. And in this case, because we've chosen a linear sliding surface, it's actually a linear state feedback problem. Okay? It's just designing a full state feedback controller S1, S2 for this particular subsystem. And I can do this if my system is controllable. I can always do this. So if the AB is controllable, then it's quite straightforward to show that this subsystem A11, A12 is also controllable. So I can design the S1 and S2. The poles of this reduced order system, I can pick any two, and they will determine an S1 and an S2, which fully designs my switching function. So here I've done it in the notes algebraically. This afternoon we will look at doing it in MATLAB, but I can choose something. Here I've chosen a complex conjugate pair. I can get my two values, interestingly S2 equals 0. And then I can begin to think about designing the controller. And for designing the controller, I will use the final equation. I know here that S dot, I can write down what it is, and this effectively is always what we've got to do. We've got the reachability condition, which is a function of S dot. We have to find S dot, and then we have to work out what control law we want to pick in terms of ensuring I satisfy that eta reachability condition. So my S dot here can be expressed in terms of the states and the inputs like this. Clearly, I've got a problem if the control doesn't come in through X3. But it does here, X3 dot, the control comes in here. And so I can choose a control which meets my requirements. It does what I say. I use the part that cancels out the bits I know. So those are known bits of the dynamics. I needn't have put that bit there. I could have used a bigger eta and my controller would still work, but I'd have a much larger discontinuity. If I do this, then this cancels directly in the S dot dynamics, and it clearly, trivially satisfies the eta reachability condition. So it's an appropriate controller. And you can look what happens. It's quite hard to see. Largely because the switching function plot here is going to 0 very quickly. So by about 0.1 seconds, it's gone to 0. I want that for robustness with that blue line. And we can see this oscillatory poles we've picked give us this system dynamics here. And actually, if we wanted to, we could show that X3 is totally determined by X1 and X2. So this dynamics here is wholly determined by S1, S2, and that subblock, the A11, A12 upper subblock of where the control doesn't act. So we want to get a sliding surface where this is 1, and we want to design a control law. And we want something which is fast initially, bearing in mind that it can't be too fast because we might well have physical limitations on the controller, but we do want to ensure S equals 0. Now, for the design, canonical forms become very, very important. And we will emphasize this this afternoon. It's interesting that some classical canonical forms naturally appear in this way. So if we look at a very classical canonical form as in 28, which we introduced to our students, it's in the form we want. It has the control input acting in the channel, the single final channel, and then it has n minus m channels where the control input doesn't act. And thus it becomes very, very straightforward to write down a sliding mode control paradigm for systems in this form. Indeed, for nonlinear canonical forms of that type, we can do the same thing as well. If we think of robotic systems, any second-order system or composed of a series of second-order systems following Newton's laws, they will typically have they'll have a position and a velocity. So they have a channel where the control input acts and one where it doesn't, quite naturally. And I think that explains why in much of the early literature, people developed these controllers for robotic systems. So for electromechanical systems, it was all the rage. This becomes more problematic. And if we fast forward to 2017, one of the things that myself and my collaborators are doing is trying to find canonical forms for interconnected, large-scale systems. We still need these same fundamental properties of being able to understand where the control signal acts and where it doesn't act, so that we can partition our problem to deal with uncertainty via the control, to define appropriate sliding modes, and to define appropriate controllers that will ensure those sliding modes are reached. These notes here go on to explain what the switching function looks like for this particular canonical form. It's very straightforward. You can see that picking a characteristic equation, it amounts to choosing the sliding surface. So the sliding surface parameters are just the coefficients of the characteristic equation. So absolutely beautiful, as long as we can make sure our system is in that form to start with. And of course, although as we've said, some are, not all of them are. So what we're going to move on to this afternoon with our MATLAB session is to start for some linear systems to start with, looking at how we can affect this change of coordinates and do very simple designs using MATLAB. Hopefully fully understanding what we're doing and why with the various sub-bits. I hope it's going to work well. As I say, my ideal would have been to have a room full of computers and me using the same computer. I'm going to have to use one computer and be using slides and MATLAB and switching between the two. But I know a number of you have got computers, but we will build on this afternoon. Before we finish, are there any questions on these very basic things? Yes. Yes. I fully get your question. And this is it is because the one is, in reality, S dot isn't 0. In fact, by switching, it's instantaneously changing with that sign, just as you've said, okay? So it is switching. In fact, it's got infinite rate of change. This is why I urge all my students and collaborators and people I work with to separate those two things, because that equivalent control signal, that notion of S being 0 is, if you like, rather like the control signal, an average argument. So it's arguing that on average, if I'm switching backwards and forwards with some band here, on average I'm S equals 0. So the equivalent control signal is a theoretical argument. It isn't the real control signal. There is not a 1-1 mapping. They are quite different. The one is an analysis tool, which is seeking to say, how do we stay in the sliding mode, and which is dealing with those, the top part of those dynamics, the dynamics where the control doesn't act. That's where it is important. To the actual control, which is forcing S and S dot to have opposite sign. And clearly, if S and S dot have opposite sign, you cannot have S dot as 0. Because it's strictly less than. Can I say sorry? Yes. Well, it depends. I mean, we will see that for some of the problems I suppose there's a big sort of push at the moment to sort of use data, isn't there? You know, people want to use data. We have lots of data, and there is a big question of, you know, do we need models? I'm a great believer in models, you know, and the fact that we don't need to know it, I don't think necessarily means it's a good idea not to use it. Because in using it, you will tailor your solution to that reachability problem much better. But it is true it is a free system. And it is true it's independent of the original dynamics. But I wouldn't like to call it model free, because I don't think this maps, it doesn't map up. You know, to me, the sliding mode control paradigm is quite different. It's quite different to other control paradigms. So in terms of language, there isn't a 1-1 mapping. There isn't a 1-1 mapping, in my view. Yes, and indeed we will see that in some of the work that we do later with higher order sliding modes. There is no need to reduce the order of the dynamics if you don't want to. There's been a lot of work in integral sliding modes, and that uses the full order of the dynamics. So it is not the case that you have to, by any stretch of the imagination. If you don't, then you will typically need more signals in order so you will have a dynamic controller typically. But there's no reason in principle why you don't have it as the order of the system, or indeed of an order greater than the system. You know, there are some controllers which actually add compensator states to the dynamics and develop sliding mode controllers. It is not important. It is only the magnitude. It is only the magnitude that is important. The actual, you know, it would have been the same if it wasn't a sinusoid. If it was some other signal that was no bigger than plus or minus 1, we would have got the same performance. It should be, well, it goes without saying that it should be bounded. because clearly nobody can deal with unbounded uncertainty, because if you have unbounded uncertainty, technically you need unbounded control, and so, you know, things fall down. So it definitely needs to be bounded, but it is purely down to knowledge of the bound, if you like, not the transient or dynamic characteristic of the signal is not important. It's only the bound. And of course, you know, there is some work that doesn't use if you don't know that bound, you know, so that you can effectively adapt that gain within your sliding mode controller. Yes. Yes. Well, certainly if we're going to use a classical linear approach, we see that we need AB to be observable, which means A11, A12 is, AB is controllable, which means A11 and A12 is controllable. I'm going to do an example with you of some work I actually did in collaboration with Technical University of Graz. It's an observer problem, but it very much shows that that is not the end of the story. In that particular case, the existence conditions don't hold. And then we have to be sensible about what we do. There are many things we can do around these kind of problems. That's why I think it's important not to get in a mindset that we have to have an A and a B that has these properties and then we do that. I mean, it's important to know that we can do that, because if we've got one, then surely that's an easy thing to do. But we have to think more widely. And just because A11, A12 was not controllable, that wouldn't necessarily mean you can't control the problem with a sliding mode controller. And in fact, for observer problems, there are several very good examples of systems which are not observable. And you can design a sliding mode observer. So controllability and observability, it is needed for certain linear implementations of linear theory, as you'd expect from the definitions, but it isn't needed for whether you can design a sliding mode control or observer, given the larger paradigm of what we're trying to do. Yep. Well, the pole location for the example I just showed. Well, I mean, even for this one, which I didn't go into detail, the poles of this system here will be determined by the switching function coefficients. So the poles of the system will be determined by the reduced order dynamics, assuming it's a linear one. So if we're designing a linear dynamics for a linear sliding surface, so we've got a linear combination of the system states, then the poles will come from that reduced order dynamics, which is a linear system, just the same as linear theory. And there will also be some poles at zero, which correspond to the reduction in order. Okay? So the equivalent control typically, so if you take the A and B and you apply the equivalent control in terms of an analysis, you will find the poles you picked for the sliding surface and M zeros for a problem with M control inputs. And though that reflects the reduced order nature of the problem. But the poles are there, they're embedded in the dynamics you picked. It becomes more difficult if you use a nonlinear sliding surface, because of course we don't have the same notions of stability. We have to use different notions. But for a linear system, the poles are just there, just as, you know, for the hot air balloon, that -1 plus or minus J, that would be the poles of that free second order system, which was the dynamics. The difference is it isn't the control that's giving you that dynamics. It's the choice of S that's giving you that dynamics.